Good morning, students. Today we will discuss Green's function for a unit ball. Before we define Green's function for the unit ball, first of all we define an inverse point or a dual point. So let us take x, a point belonging to n-dimensional real Euclidean space, and this point x is non-zero. Then the point which is dual to this point x, that is defined by x bar is equal to x upon x mod square. This is called dual of x with respect to the unit sphere. Now, next we define Green's function for a unit ball. To define Green's function for a unit ball, let us take a point x belonging to the unit ball, and x is non-zero point. Unit ball means the set of all those points y whose distance from the center of the ball is less than the radius. Radius of unit ball is 1. So we can say that unit ball is the set of all those points y such that y mod is less than 1. Now because we are to define Green's function for the unit ball, so before defining this function we will have to find corrector function having no singularity in the unit ball. So let us define a function phi x, which is the function of y. Here y belongs to the unit ball. We have defined this function by phi of x mod into y minus x bar. Here phi is fundamental solution of Laplace equation. X and y are different points. Now we check that this function which we have defined, this has no singularity in the unit ball. Now because x bar mod, by definition of x bar is x upon x mod square. So its absolute value is 1 upon x mod. Now because x belongs to the unit ball and x is non-zero, so by definition x mod is less than 1. So its reciprocal will be greater than 1. So this is greater than 1, and therefore we can say that the point x bar does not belong to the unit ball. And this function which we have defined, this function is having only one singularity at x bar, and because x bar does not belong to the unit ball, so we can say that the function which we have defined, that function has no singularity in the unit ball. Now because if we find the Laplacian of this function, that will become Laplacian of this function phi, and this phi is fundamental solution of Laplace equation. So we can say that Laplacian of the function phi x, that is 0 in the unit ball. Now if we take any point y belonging to the boundary of this unit ball, then the value of this function is given by 1 upon n minus 2 alpha n into x mod raised to the power n minus 2 into y minus x bar mod raised to the power n minus 2. Now this term can be split into two parts. Y minus x bar mod raised to the power minus 2, that can be taken in the numerator, and also from here x mod raised to the power minus 2, that can be taken in the numerator. So we can write it as x mod square into y minus x bar mod raised to the power 2 upon n into n minus 2 into alpha n into x mod raised to the power n into y minus x bar mod raised to the power n. Now let us consider the term x mod square into y minus x bar mod square. Now y minus x bar mod square means the dot product of y minus x bar with itself. If we simplify this product, this term as it is, this will become y dot y minus 2 times x bar dot y plus x bar dot x bar. Y dot y means the square of magnitude of y. X bar dot x bar means the square of magnitude of x bar. Now because y mod is 1 and the value of x bar, that is x upon x mod square. So this can be written as x mod square minus 2 times x dot y plus 1. 1 is y mod square. So this becomes y minus x mod whole square, taking square root on both sides. So we have obtained x mod into y minus x bar mod is equal to y minus x mod. Here y belonging to the boundary of the unit ball. Now we can put this value in the function which we defined phi x phi. So that will become y minus x mod square upon n minus 2 alpha n into y minus x mod raised to the power n. From here, after simplification, this can be written as 1 upon n minus 2 alpha n into y minus x mod raised to the power n minus 2. Now by definition, this is phi of y minus x. So we have proved if we take y belonging to the boundary of the unit ball, in that case the function phi x phi, this is phi of y minus x. Similarly, in the case when n is 2, we can again prove that the value of this function phi x phi, that is phi of y minus x. So we can say that the function defined by us by this formula, that is the corrector function, having the property that the Laplacian of this function is 0 in the unit ball, and on the boundary of the ball the value of this function is phi of y minus x, and this function is having no singularity in the ball. So we have obtained a corrector function in this case. Now we are in a position to define Green's function for the unit ball. By definition, Green's function is defined as phi of y minus x minus phi x phi. This is fundamental solution of Laplace equation, and this is corrector function. Now by our definition of corrector function for the unit ball, this is phi of x mod into y minus x bar. So this gives us Green's function in the unit ball. Now by using this definition, we can find a representation formula in the unit ball for this boundary value problem. Laplacian of u is equal to 0 in the unit ball, and on the boundary value of function u is g. So let us solve this boundary value problem. So to solve this problem, let us take u, which is twice spontaneously differentiable function defined on this unit ball. Suppose this u is the solution of this boundary value problem. Now we already obtained the solution of the boundary value problem for the Poisson's equation. So here in our present case, the value of function f, that is 0. So in that formula, if we put f is equal to 0, we get the value of u at x, which is given by minus integral over the boundary of unit ball of the function g into curl g by curl nu. Here nu is unit normal outward drawn vector to the unit ball. Now we have to find curl g by curl nu, where y belongs to the boundary of the unit ball. So let us find curl G by curl nu. Now by definition, curl G by curl nu means dg dot nu. The components of dg means gradient of g with respect to y. It is having the components curl G by curl y1, curl G by curl y2 and so on, curl G by curl yn. Nu is the vector y upon y mod. So its components will be the components of y divided by y mod. So this dot product will become summation yi into curl G by curl yi. This is the value of curl G by curl nu. Now we are to find these partial derivatives of g with respect to yi. So let us find by putting the value of Green's function which we defined for the unit ball. So this will become curl by curl yi of the function phi of y minus x minus partial derivative of this function with respect to yi. This phi is the function of x mod into y minus x bar. Now let us find these two derivatives one by one. This derivative we have already derived in previous article also. So we will put the value directly from there. So the partial derivative of this function phi with respect to yi, this is given by negative of yi minus xi upon n alpha n y minus x mod raised to the power n. This is the value of derivative for n greater than equal to 2. Now let us find the derivative of this function with respect to yi. So let us consider the partial derivative of this function phi with respect to yi. Now by definition of function phi, this is given by 1 upon n minus 2 alpha n x mod raised to the power n minus 2 into y minus x bar mod raised to the power n minus 2. Now this part is independent of y. So it means we are to differentiate only this term with respect to yi. So differentiating this term with respect to yi, we get the partial derivative which is given by minus 1 upon n alpha n x mod raised to the power n minus 2 into y minus x bar mod raised to the power n minus 1 into curl by curl yi of y minus x bar mod. This is the value of y minus x bar mod. So its derivative and when it is simplified, we get the value of partial derivative which is given by negative of yi into x mod square minus xi upon n alpha n x mod raised to the power n into y minus x bar mod raised to the power n minus 1 into mod of y minus x bar. So we have obtained this value. Combining these two terms, this can be written as y minus x bar mod raised to the power n. And similarly you can find the value of this derivative for n is equal to 2 also. Now if y belongs to the boundary of the unit ball, in that case x mod into y minus x bar mod is equal to y minus x mod. We have already proved this. So we can substitute this value in the partial derivative of function phi with respect to yi. So putting this value here, this will become minus of yi into x mod square minus xi upon n alpha n y minus x mod raised to the power n. Now we can substitute these values in the partial derivative of g with respect to yi. So putting values there and simplifying, we get the value of curl g by curl yi which is given by minus yi into 1 minus x mod square divided by n alpha n into y minus x mod raised to the power n. Now what was curl G by curl nu? That was summation yi into curl G by curl yi. And we have obtained the value of curl G by curl yi. So we can put that value here. And simplifying this summation, this term is independent of summation. Yi into yi, that is yi square. So summation yi square, yi's are the components of the vector y. So summation yi square means y mod square. And because y is belonging to the boundary of the unit ball, so its magnitude will be 1. So y mod will become 1. So we have obtained the value of curl G by curl nu, which is given by negative of 1 minus x mod square upon n alpha n y minus x mod raised to the power n. So we have obtained the values. Now we can substitute these values in the equation second. So from there we get the value of u at x, which is integral of the function g into 1 minus x mod square upon n alpha n y minus x mod raised to the power n. This integral is over the boundary of the unit ball. This is a representation formula for the given boundary value problem in unit ball in terms of Green's function. And we can write this formula in terms of kernel also. So if we define kernel given by this quantity 1 minus x mod square upon n alpha n y minus x mod raised to the power n. Here x belongs to the unit ball and y belongs to the boundary. So by using this, the representation formula becomes u at x is equal to integral of the kernel k into the function g over the boundary of the unit ball. So this is the solution of the given boundary value problem in terms of the kernel k, which is the function of x and y. So this is the kernel of the unit ball. So this completes a representation formula for the given boundary value problem in the unit ball in terms of Green's function.